right, let's look at some examples of problems involving operators on vector spaces. So in this case, our first operator is a linear operator. Pretty much we're going to use mostly linear operators. Well, actually, we're only going to use linear operators. Most of the operators will be just matrices. So A times X, A is of dimension 2 by 3. It's this matrix. Basically, it's an identity and then 0. So we can go through and show that the kernel is given by this, that is the null space. I can take this matrix, multiply by this column, and get 0. And this null space is non-trivial. Okay, it's non-trivial because it's not 0. Okay, and yet multiplying it gives 0. So there's an example of null space. Here's another matrix. In this case, it's just a row. And I have some vectors that I can use to test. So this vector, if I multiply this row by this column, I'll get 1 times 1 minus 1 times 1 is 0, plus 1 times 0 is 0. So this gives me 0. This shows that V1 is in the kernel of A. If I take this row and multiply by this column, then I'm going to get 0 times 1 minus 1 times 1 plus 1 times 1. That gives me 0. So that shows that this is also in the kernel of A. But what about this guy here? What about this guy? If I take this row times this column, I get 1 times 2 minus 3 plus 1 gives 0. So this actually is in the kernel of A as well. And actually, I could go through and show that if I take this column multiplied by 2 and add this column, I will get this column. Okay, so it's actually a linear combination of these two columns. All right, so that's some null space examples. Identity. The identity operator maps X back onto itself. So X is equal to I times X. And so for matrices, the identity matrix is all ones along the diagonal and zeros off the diagonal. So that is, and so we often will use the identity with the subscript n to indicate the nth order identity. The inverse operator. So here our operator G is the matrix A. So the output Y is equal to A times X. So X gets multiplied by A and gives Y. So for this example, we're going to use this matrix A. The inverse function takes Y and gives you back X. Okay, so that's what we have. It's an inverse map. And I can show that for this matrix, this is the inverse function. So the inverse function here, we can use standard linear algebra tools to get the matrix inverse. And I can go through and show, using this, that if I take this A matrix and transform X into Y, some vector X into Y, and I use this inverse matrix, I will get back to the exact same X. And in fact, because I go from X back to X, the result is just the identity matrix. And I can go through and show that if I multiply these two guys together, I'll get the identity. A matrix times its inverse is always the identity. So that's the definition, and so we can see that here. All right, what about the adjoint operator? That's a little more complicated. So if we assume a matrix like this, what is the adjoint operator for G of X equals to A times X? Well, it turns out it depends on your definition of inner product. So if you remember, the inner product was defined implicitly in terms of inner products. I'm sorry, the adjoint was defined in terms of inner products. These two inner products must be equal to each other. So let's take a look at this. So if we use this inner product, which is the inner product on the output space, as Y transpose this, which is that, and if I multiply it through, I can go through and show this. So here, multiplying this out, I get this expression. Notice that I have Y's multiplying sums of X's. I can rewrite this equation so I get X's multiplying sums of Y's. And I can go through and show that this can be written as X transpose times a column, and I have these elements in there, times Y. So I can go through and show that that quantity there can be written this way. And so if we define the inner product on the input space this way, I can show that the inner product on the output space is equal to the inner product on the input space. And so this then is the adjoint of the matrix A for these definitions of inner products. What happens if we change the definitions of inner products? So if instead we use these definitions, instead of having W transpose X, we have W transpose M times X. I can go through and show that this defines an inner product on the input space. I can define an inner product on the output space this way for another matrix M N. And so I can show that this indeed satisfies the 4 defining properties for an inner product. So in this case, we must have that the inner product on the output space is equal to the inner product on the input space, where we don't know exactly what A adjoint is yet. And we saw before the A adjoint was just A transpose, but in this case it won't be because we now have a different definition for the adjoint. Okay, so alternately we can do it this way. Instead of saying that the 2 inner products are equal to each other, we can say that their difference is 0. 0 is equal to the difference of the 2. So here's the first inner product. This is the second inner product. And I notice that both of these guys have Y transpose on the right and X on the left. I'm sorry, Y transpose on the left, X on the right. I can factor out that Y transpose on the left and the X on the right and give this expression. And so all of this must be equal to 0 for all X and Y. Okay, for all X and Y, this expression must be equal to 0. So in order for this to be true for all X and Y, in particular, it means that this stuff on the inside must be equal to 0. This implies that this is equal to that. Okay, and now I can solve for A adjoint. I can first do that by multiplying through on the right by M inverse. Okay, and then that gives me this stuff, and then that would leave me A adjoint transpose. Taking the transpose of that now gives me this expression. I can now take the transpose of this product, and this is what I get because of the fact that M and N are both symmetric matrices. I get this expression. And so for the values of M, A, and N, I can go through and show this is the adjoint that I get. And this is clearly not the same as A transpose. So this is a different adjoint because we have a different definition of inner product. All right, what about convolution operators? So what about a different linear operator? Okay, so we talked about using this for matrices as linear operators. What if we have a different linear operator? So suppose we now have a convolution operator. That is, we're working with different quantities now. So if we let V, the input space, be the space of continuous functions defined on this interval from 0 to 1. So it's a function that's continuous over this interval. Now, if you recall, in any interval, there are an infinite number of values in that interval. No matter how big the interval is, there's an infinite number of values. And so this function basically assigns a value to every value along this axis. So there are an infinite number of values along here. Continuous function means that it's connected. You know, there can't be any breaks in it, right? So we'll let also there be a little g function that is also a continuous function on the same interval. And so for u in the input space, we can define the operator g this way. It's a convolution. Okay, g of t minus tau, u of tau, d tau. Okay, so g operating on u at some value t is defined as this integral. And notice that when we're done, we get something in the output space. Okay, now the output. So when we do this integral, we get a value, a number. So even though it looks really complicated, we don't even know what g and u are. Turns out we don't actually have to know them to still work with them. But when we integrate, this just comes out to be a number. So the output space is actually just real values. So here's our input space, space of continuous functions. Here's our output space, the real values. I take a u, I map it through g, that's going to give me a real value. I'm going to take that value, map it through the adjoint, and get now a function, a space of the continuous functions. Okay, so it's Notice that here, G is taking an infinite, a function that something has an infinite number of values and giving a number. G adjoint is taking that number and generating a function that has an infinite number of values. Okay, so this is one way of doing that. Okay, G adjoint of y of tau is given by this. So between 0 and t, for tau between 0 and t, I get this expression. I get zeros for t, for tau greater than t. Okay. So again, y in this case is given by this integral from u. So I got u, it's going to give me y. And so y is going to go in here. And so u tilde now is given by this expression, where y is given by this. All right. So what's actually going on here? So I have this function u that's going into my system, a system that has impulse response g. The output then is this convolution. Okay, so that's what we have for our system function. And so given y then, which is just a number at any given time t, there's just a number, then u of tau, u tilde, is given by the adjoint of that, which again is this function. All right, so now we want to see, does this definition actually work as an adjoint? Well, the way to tell is you check the inner product on the input space, the inner product on the output space, and see if they're equal. All right, so let's see what's going on. So the inner product on the input space, remember the input space is a space of continuous functions. We can define this as an inner product, as an inner product. Again, there's more than one way of defining the inner product. This is one way of defining that inner product. So the inner product on the output space, remember the output space is in the space of R. I have this expression. And notice, since the inner product is on the space R, these are just scalar values. So their inner product just ends up being their product. Okay, it's just their product. So this quantity we saw was given by this integral. Okay, I can take the y inside the integral and I get this expression. So I have an expression for the inner product on the input space. Now what about the output space? So the inner product on the output space is remember, this is u tilde times u dt. So notice that the inner product on the input space is not a convolution. It is just the integral of a product. Okay. So we also make note of the fact that this function, the way it was defined, was 0 for tau greater than t. And so this integral, instead of going from 0 to 1, goes from 0 to t. This quantity, if you recall, was just g of t times y of t. And so when we actually compared the two inner products, the inner product on the input space, inner product on the output space, we see these two are in fact equal to each other. And so we have effectively shown that that formula for the adjoint is actually the adjoint. So we've seen now how to work with functions that are much more complicated than just a simple matrix problem. All right, we're going to move on now to projection operator. Projection takes something from some space, maps it into the same space, but not just anything within that same space. It maps it into a specific region in that space, such that any value in this region maps back into that region. So there's hidden in here is actually a region that is actually the range of this space through the projection. So one way of looking at this is using the this example. If our vector space is all of R3, and I have a subspace of that, which is just R2, that is, it's the xy plane within the three-dimensional space, I can go through and show that this projection operator will project things from three-dimensional space onto the xy plane. So it's kind of like casting a shadow onto that xy plane. So if we now have a subspace spanned by some vectors, v1 to vl, we can form a matrix from those vectors. This matrix will be of dimension n by l. So each of these columns, remember, it had n elements in it. So this is n and l columns, so that's why I get n by l. If I now take this matrix and form this matrix, this becomes a projector. I can show that this is a projector, that it is symmetric and that it is idempotent. That is, I take this, multiply it by itself, I get the original matrix back. And this projection will map on from Rn onto the subspace M. So by way of example, suppose M is the span of this column, just a single column. Okay, so I can form now F from this subspace. In this case, I just let F be this column. I go through and do this calculation. The E that I get will be this. Notice that if I had chosen some multiple by this column, it turns out all of that would have canceled, and I would have still gotten this same exact same matrix. Okay, I can see that this matrix is symmetric. Okay, this element is equal to that element, this element is equal to that element is equal to that element. And if I were to multiply this matrix by itself, I would get itself back. So I've shown this is a projection onto that subspace. Also, I can see it's a projection because if I look at each of the columns of this matrix, each of the columns is a multiple of this column. And so that shows that we have the result, that this will actually project onto that subspace. Regardless of what I multiply by this is what multiplying a column by this matrix, I'm going to get a linear combination of these columns. But each of these columns is a multiple of that. So a linear combination of these columns is just going to give a multiple of that column. And so I can see that this projection maps onto this subspace. Okay, so that is one of the powers of projectors, is they maintain subspaces. So this is practice problems for linear operators.